start the class. So I hope it is visible, plate contactors in PPT mode.
Yes, ma'am.
Right. Thank you. So good morning to all. In today's class, we will continue the discussion on distillation column design. But before proceeding further, let me revise the last class. In the last class, we mainly focused on plate efficiency. Some basic about that plate efficiency that you have already read in your mass transfer course, and in detail how to count the uh, plate efficiency considering different parameters like mass transfer characteristics, geometry of the plate, etc. Considering that, we have discussed a few methods to find out plate efficiency. Okay, so plate efficiency that is for the what we can say the how the mass transfer is occurring on a single plate, it counts that. Okay, along with that, we have discussed the column efficiency also. The column efficiency, which basically counts the that what is the overall column efficiency. Okay, so if you have number of ideal trays, you can find out the real trays. Okay, so that is the overall column efficiency we have discussed considering O'Connell's method. And apart from this, for plate efficiency, we discussed the AICHE method, and this AICHE method first counts the point efficiency, and then there is a relation uh, or there is a graph between point efficiency and plate efficiency, and that is with respect to slope of equilibrium and operating line, like that. So, considering all these parameters, we can find out plate efficiency using AICHE method, which considers many more parameters than only the what we can say the concentration change. Okay, so that was about the plate efficiency, and now we will proceed towards the design of a single plate. Okay, or the what are the plates, different plates which are used in distillation column, and how we consider design of a single plate. That's all. All those points we will discuss over here. Okay, so let me start with plate contactors, like how the contact between vapor and liquid occurs over the plate. Okay, that we will count first, and then we will proceed towards plate design. Okay. So as far as plate contactors is concerned, this is the schematic to discuss the contact between liquid as well as vapor. Okay, so that a few points about that we have already discussed in previous lectures, and some more is what we can say in detailed discussion we will consider the this schematic. Okay, so for a single plate, if I tell, for a single plate, this is the single plate, this is the single plate, and similarly this is the single plate. Okay, so single plate, when I'm considering, there are different factors which we need, which we use to count. Okay, so when we consider this, uh, this is a single plate, and if you consider this particular section, this is nothing but the wear height, right? That we have discussed, and this zone, okay, this zone we call as the uh, apron, downcomer apron. This zone is called as downcomer, and this vertical line you can see, this is nothing but the downcomer apron. Okay, and we have already discussed uh, about the active area in AICHE method. Okay, before we have already discussed. Now here you can see very easily what is the active area. Active area is basically, we also call that as the bubbling area. Okay, where holes are available. Okay, so if you consider that this particular downcomer, okay, downcomer in this the that whatever liquid is flowing over this, as you can observe over here, whatever liquid is flowing over the plate, it will pass through this. Okay, it will pass through this downcomer to come to the bottom plate, or below plate. That point we have already discussed. Okay, now what is different over here? The difference is, if you consider this downcomers area, either this area or this area, at the bottom you will see the liquid, right? At the bottom you will see the liquid. However, at the top we have this what we can say, bubbles. Okay, or we can say vapor. Okay, so what happens when liquid is coming to this and flowing over this plate and passing through this plate through this weir? Not only liquid, because here I'm having the vapor and liquid mixture. Okay, because interaction is important over here to occur, and because of that interaction, vapor and liquid, what we can say, they are not available in different phases, they are mixed. Okay, phases are there, but that phases are mixed to it. Okay, so when liquid comes down over this weir, this what we can say, bubbles are also coming with the liquid, or the vapor is also coming with the liquid. Okay, now here you can say we have the froth, and here also we have froth. Okay, so every downcomer has the same situation. Below we have the liquid, and above we have the froth. Okay, now, this section between, or this distance between two plates, uh, this distance should be sufficient so to have vapor liquid separation. Okay, so what is the point to consider over here? That when the liquid is coming to downcomer section through this region, sufficient residence time is required here for vapor and liquid to disengage. I hope you are getting my point. Okay, so that vapor moves up and liquid comes down, and liquid is not sorry, vapor is not allowed to come to below tray. Okay, or the below plate. Little bit it may come, but here this distance depends on that. As liquid and that froth is moving, we should have enough time to disengage this froth and liquid. Okay, and so that liquid will come over the below plate only. Further, when we consider this tip, this plate, liquid is moving above this, right, in cross flow. However, when we consider the vapor, vapor is coming from the bottom plate and moves upward. So through these holes, vapor moves. Okay, and these through this hole vapor moves means these holes are available only in the active area. And you understand what is the active area? Active area is the area between two downcomer, from inlet downcomer to exit weir. Inlet downcomer to exit weir. I hope you are getting. So this is nothing but the active area. Here the active area is basically shown over from here to here, but actually it is uh, between inlet downcomer to outlet weir. From here to here it should be. Okay, because uh, once I'm having the active area, okay, active area is how we have calculated before in plate efficiency. That is basically cross sectional area of the column minus twice of downcomer area. Okay, so one area is this, another area is this, twice of downcomer area. And usually the downcomer area is same throughout. It's not like somewhere it is less, somewhere it is more. No, it is same. And uh, uh, active area is between inlet downcomer to outlet wear, right? Now, when the liquid is coming from the bottom, from above plate, here we consider that no holes should be available. Okay, because liquid should stay over here and then it will move towards this. Okay, if we will prepare the holes here, liquid will start dipping from here. Okay, coming down from here. Okay, which we do not want. We want liquid to move over this plate, right? So this is the section where holes are not available. Similarly here the section is available where holes are not available. So all these sections over the plate which does not include any hole, that we call as calming zone, right? That we call as calming zone. And the actually whatever active area is shown over here, this is exactly not the active area. This is the perforated area. Okay, perforated area. Active area is what? The cross sectional area minus twice of downcomer area, right? Active area minus calming zone area will give us the perforated area. So exactly whatever shown over here, uh, the active area, that should be perforated area. All these parameters we will discuss in design in detail, but you should understand the geometry first. Okay, and when the vapor is coming, passing through these holes, these vapor come across with the liquid and it penetrates the liquid and moves upward. Okay, penetrates the liquid and moves upward. And accordingly accordingly the interaction will occur between liquid and vapor and mass transfer proceeds. Okay, so when the vapor moves upward, because that is the normal tendency of vapor, it will always move upward. Okay, so it passes through the liquid and move upward. However, when it moves upward, it takes some of the liquid droplet with it, and that we can see in the form of froth and spray. And you can consider that we have sufficient distance between two plates. Okay, it means it has sufficient space, sufficient what we can say, sufficient height to have disengagement of liquid and vapor, so that liquid will come to this along with certain froth, as you can see over here. So residence time will required over here as well as here. Okay, so that gap between the plate is very important, and that we call as plate spacing. Okay, so that is again the design parameter that we will discuss. Okay, so in that way you can consider the uh, you can consider the contact between vapor and liquid over the plate and how the movement occurs. Further, uh, if I tell you that if vapor movement or vapor velocity is too high, okay, if vapor velocity is too high, okay, it will take liquid with it, right? It will take liquid with it and it will push liquid to downcomer to move upward. Okay, please try and understand. If I'm talking about vapor velocity, the vapor velocity, if it is very high, it takes the liquid with it towards upward. Okay, from this side also and from downcomer side also. And it will push liquid to move to above plate where already liquid is available. I hope you are getting my point. Okay, where already liquid is available and this vapor pushes the below liquid to move upward. Okay, in that way there is a tendency that hold up or liquid filling will start in above plates. Okay, and that we call as the flooding condition. Okay, it means the vapor velocity should not be that high so that flooding will occur. Otherwise, everywhere liquid is there, and the what we can say, the interaction between vapor and liquid is not possible. Okay, so liquid velocity should not be too high to have what we can say, flooding. Okay, that is one point. Another point is if vapor velocity is too low. Okay, if vapor velocity is too low, what is the meaning of this vapor will not be able to move through these holes. Okay, and we have discussed before also that vapor is only the what we can say, the entity which holds the liquid over the plate, which does not allow liquid to move down. And if vapor flow is too low, liquid will start dipping or coming from these holes to downward. Okay, it means again it will not allow vapor to move up. Okay, so it means the vapor will move over the plate also, vapor will pass through the holes also, and vapor will pass through downcomer. Everywhere vapor is moving. And when the vapor, when the, sorry, everywhere liquid is moving, sorry. Okay, so liquid will start coming from these holes to downward. Okay, and that condition we call as weeping condition, right? Flooding condition when liquid pushes upward by the vapor, and weeping condition means when liquid pass through the holes and vapor is not allowed to move up through the holes. So that we call as weeping condition. Both conditions depend on the vapor flow only. Okay, so the maximum velocity of the vapor that can be fixed by flooding condition, one point, right? Minimum flow of velocity can be controlled or can be fixed by weeping condition. So all these conditions we need to check when we are going to design a single plate, right? So that these are some points. Another point is why I'm emphasizing so much on this particular schematic, because based on that the further discussion you will be able to understand. Okay, so if I consider this uh, vapor liquid flow again, so in that case, uh, okay, when weeping will occur. Okay, weeping will occur when liquid flow or liquid flow is less and vapor flow is, sorry, vapor flow is less and liquid flow is more, then weeping condition will occur. Okay, further, if let's say liquid is moving on its over the plate, no problem. But if vapor flow rate is too high, okay, vapor flow rate is too high, one thing is it pushes the liquid upward, that is the flooding condition. Further, if vapor flow rate is again more than that, if vapor flow rate is much more than that, flooding is occur. In that way, vapor passes through the liquid without having any interaction, and that is called as the movement of jet. Okay, it is a jet like type of condition where vapor passes through these holes and move very with high velocity through this liquid. Their interaction is also not possible. Okay, because it passes through the liquid without having any interaction. Okay, or we can say it makes the hole like a jet and moves upward. Okay, that condition is called as coning condition, CONNING, coning condition. Okay, so all these points we need to discuss. And as I have told you that uh, as flooding will occur, before flooding entrainment occurs. Okay, and then flooding will occur, and beyond flooding we have coning condition. I hope you are getting all this and try to relate. Okay, another point is when I'm considering this downcomer and the liquid and the froth is coming together to this downcomer, and uh, what we can say, liquid is uh, not allowed to separate. Okay, liquid is not allowed to separate, then the froth will come with this liquid over the plate. Okay, so in that way, what we can say that that is obviously undesirable condition. Vapor should move up, not to down with the liquid. Okay, so in that way, we consider that downcomer backup should be checked. Okay, downcomer backup means that downcomer, whatever liquid and froth is available, it should have sufficient residence time so that separation between vapor and liquid is possible. Okay, so we have seen different conditions over here. Okay, number one, weeping. Number two, entrainment. Number three, flooding. Okay, number four, downcomer backup. Number five, coning. I hope you are getting all this. So we will consider uh, all these parameters in design. Okay. However, if you consider the flooding, and that if you maintain the flooding condition, it means flooding is not allowed. In that case, what will happen? In that case, coning will also not happen, because coning will happen when velocity increases the vapor velocity at which flooding will occur. Okay, however, certain entrainment is possible. So entrainment, flooding, weeping, these are important parameter along with downcomer backup. These are four parameters which we need to consider. Okay, and but we do not consider coning, because that we understand that if flooding is not occurring, coning will not occur, right? So in that way, you can have the uh, uh, different conditions over here through this schematic only. And I hope all these points are clear to you. Okay, and uh, so as far as plate contacting is occurred. Okay, we first see how many types of plates are available, and then we will proceed towards the uh, plate design. Okay, and all these plates are called as contactors. Okay, because contact is required between liquid and vapor. So basically, plate contactors are divided in three different ways. Number one, sieve plate. Number two, bubble cap tray or plate. And number three, wall tray and wall plate. Or, okay. So in this way, you can have three different plates which are usually considered in distillation column in industry. Okay, so we will start with sieve plate and proceed further, and we will see merits and demerits of each along with their geometry, along with their um, design part. Okay, so let me start with the sieve plate. If you have any confusion, please discuss. Okay, just 1 minute. So so this we have already discussed. So let me start with the sieve tray. So as far as sieve tray is concerned, it is a simplest type of tray used in cross flow contactors. Okay, cross flow, how we are considering cross flow, that you know that liquid is moving in this way horizontally over the plate. Okay, and vapor is moving vertically through these holes. Okay, or through the liquid. So therefore the contact is always cross. Okay, so sieve plate is the simplest type of cross flow contactors, and it is also also cheaper than other like bubble cap and wall plate. Okay, if it is simplest, it should be cheaper as well. Okay, so which tray we call as sieve plate or sieve tray? These are simply the metal plates with holes in it. Okay, like if you have metal plates and you prepare the holes in this, that we call as the sieve tray. Okay, as you can see over here. Okay, this is a very simple type. Simply plate is there and we have the holes, and you can see here this is the section where holes are not available. So this is calming zone along with the periphery. It is not visible clearly over here, but some section we used to what we can say leave. Okay, and this is the wear, and the bottom part of this black section, it is called as downcomer apron. Okay, so this section is downcomer, and here we have the liquid is coming from above plate and moves over here. Now if you consider this particular section, okay, this is called as manholes. Okay, for maintenance purpose, what we can say, operator or the industry people uh, can come inside the distillation column. Okay, so this is called manholes. Now if you are considering different sections, here I'm having, this is one section, this is another section, this is another section, this is another section. The point is that if plate diameter is too large, okay, instead of using a single metal plate to make the holes, we usually have the holes over this uh, in different sections, and these sections are joined to each other. Okay, so this you can consider as the connection between different sections of the plate. Okay, to make this whole plate. Okay, and further, if you consider this particular section or this particular section, the plates are what we can say attached side by side. Okay, so how these plates are connected? These plates are connected by what we can say backing strip. Okay, backing strip. You know that we have discussed. Where that we have discussed in the last CED1 course when we were discussing about joints. Okay, so in this case, these two plates are arranged side by side, and below this, a metal plate is welded. Okay, which because these plates has to be at the same level. Okay, so therefore we can consider the back in these sections which are placed just one after the another, just beside. Okay, side by side these are arranged, and below we have the metal plate, and that we call as the backing strip that is welded. Okay, so wherever that welding is done, wherever the backing strip is done, there also holes are not available. Okay, at the periphery holes are not available. Okay, here you can see the holes. Okay, but the hole for mass transfer, that is not provided, that is not available at the periphery. Okay, the reason being, if I ask you that how the plate is attached to the distillation column, okay, how you can imagine that attachment? Okay, because these are already attached at inner periphery, right? So how these plates are attached, like if you consider this particular section where plate is available. Okay, this particular section, uh, we consider a ring, a metal ring. Okay, we consider a metal ring of this shape only. Okay, and that metal ring periphery of the distillation column, and over that inner periphery this plate simply sits, or this plate stays there. Okay, and to have the, what we can say, the proper joint, we used to bolt this in periphery, or we can say this particular section, to the plate which is welded at inner periphery of the distillation column. I hope you are getting my point. Okay, however, that part or that ring is not available in downcomer section. Otherwise, it will create hindrance in the movement of liquid through downcomer. Okay, so as I'm having this, what we can say, periphery of the plate in the same, uh, what we can say, uh, same design, the periphery will be available, or it is welded at inner diameter of the column. Okay, and over that this plate stays, and these are bolted. So some holes you can find of that these are bolted. Okay, because of the bolt also some holes are made. So all holes are not available for what we can say, for mass transfer. Therefore, removing all these sections where holes is not possible, you understand, right? If strip is there, or ring is there, their hole cannot be made. Okay, holes cannot be made. Holes can be made only in the section which is free, okay, in the plate. Therefore, uh, if you consider the this particular section from here to here, okay, this particular area we call as the active area. Okay, however, removing the calming zone area, this is calming zone only, this is calming zone. Okay, the backing strip is available, that is calming zone. Okay, at inner periphery ring is available, that is calming zone where holes are not available. And similarly, we can have some section of metal sheet which we do not allow the holes to make, because otherwise liquid will start uh, l- otherwise we can have the vapor movement from there also, and it will take again the liquid to move upward and put hindrance in the movement of liquid to downcomer. Okay, so therefore all these sections have certain calming zone. Okay, so active area minus calming zone is the perforated area where holes can be made. Okay, I know I'm taking too long to explain that, but that is mandatory for you to understand. Okay, it will be easier for you to go for the design directly. Okay, so I hope you are getting this, that what is active area, what is perforated area. Okay, and if you consider the area of this particular plate, okay, if you consider area of this particular plate, this is called as net area. Okay, that is another area. Net area is there, and net area you can calculate as cross sectional area of the distillation column minus downcomer area only once. Okay, so this whole plate area we can consider as net area. Okay, this area from inlet downcomer to outlet weir, this we call as the active area. Active area minus calming zone area will be called as perforated area. Okay, and cross the column area, that is already the known parameter to you. Okay, so in this way we can have the detailed discussion about different sections, different areas in the plate. Okay, this is not only true for sieve plate, this is for all plates, right? And C plate, that you understand, that is the, we consider as the metal plate with holes, the very simple type of geometry. Vapor passes straight upward through the holes. The liquid on the plate. Okay, so whatever liquid is available, okay, whatever liquid is available, it flows over these holes and mass, and the vapor is coming down, and that passes through the liquid which is available on the plate. Okay, that's why it is called as cross flow. Okay. Yes. Next is, as there is no vapor liquid seal. Okay, so there are chances of weeping in the liquid in the lower flow rate, which reduces the plate efficiency. Okay, now the point is, when we consider this sieve plate, this is nothing but the metal plate where holes are available, and uh, through this hole, vapor is coming from the bottom and it interacts with the liquid. However, if that flow rate is less, okay, or vapor, what we can say, vapor flow or vapor velocity, we can say, uh, uh, if that would be lesser, okay, in that way the liquid will start moving down from these holes. Okay, and that we call as weeping condition, we have already discussed, which is completely undesirable condition, because it will block the path of vapor to move, right? So weeping condition we should not allow. However, in this sieve plate, there is no provision for liquid to stay over the plate. Okay, if vapor velocity is less, liquid will start moving down. Okay, so that is the limitation of this sieve plate. Okay, because if vapor flow is because um, that can be that can occur, right? If vapor flow rate is low, and that can occur in the distillation column. Okay, you cannot say that the vapor flow should be at this level only. No, you can say that my plate should be in such a way so that whatever the flow of the vapor is available, weeping should not occur. Okay, so that is the limitation with this sieve plate, that liquid should sorry, that is the limitation of this sieve plate, that vapor flow rate should not go, or what we can, should not be less than the desirable velocity where weeping should not occur. Okay, so what is the point, that we should not use sieve plate when we are dealing with low flow rate of vapor. Okay, therefore this is mandatory to check this vaping condition. We will discuss all this in detail design. Okay, so far we are only uh, uh, right now we are only discussing the conditions. Okay, but how that conditions will be met during the design, that we will see. Okay, so the limitation of C plate is the low flow rate of vapor cannot be allowed, or cannot be handled in this C plate, right? Another point is, it has lower fixed cost as well as lower maintenance cost relative to bubble and valve tray. So that these trays also we will discuss in subsequent slide, but these trays should have C plate has the lowest fixed cost, therefore it is cheapest as well as simplest. Okay, but of course there is a limit to operate. Okay, so if you consider a C plate, it is nothing but this type only. Okay, you can have metal plate where holes are available at regular interval. Okay, right. And if you consider the center of this and center of this point, you can, these two centers you can join. So this is called as a hole spacing. That is again the important parameter. Okay, and hole size is again the important parameter. All these we will discuss. Okay, but I hope you understand what is C plate, and what is the operating behavior in the C plate, and what is the limitation of this C plate. Okay, now, once I'm having the limitation of C plate, that it cannot handle the low flow rate of vapor, we have another plate which we call as bubble cap plate to allow the to what we can say, uh, to address the limitation of C plate. Okay, so let's discuss. So when we consider this bubble cap tray, in this type of plate, in this type of plates, a number of bubble cap is fitted. Okay, so we will first understand what is this cap and what, uh, how, why we call that as bubble cap. Okay, cap, you understand? Okay, how, why we call that as bubble cap, that we will see. Okay, so bubble cap tray has a riser or chimney fitted over each hole and a cap that covers the riser. Okay, so if you see this particular schematic, uh, here you can understand, just a moment, here you can understand that. Okay, so this is basically the hole. Actually, hole is available from here to here, that you can see. Okay, from here to here. Okay, so that hole is available, and inside the hole, we weld one nozzle. Okay, nozzle means this is simple cylinder, nothing else. Okay, so this nozzle or this cylinder has sufficient height, and therefore we call that as a riser. Okay, this is the riser. Okay, and over that riser we have that bubble cap, which is just what we can say, that bubble cap stays over here. Okay, or we call that as cover. Okay, now the point is, if let's say vapor is coming from the bottom. Okay, if vapor is coming from the bottom, it passes through this chimney or riser. Okay, otherwise there is no other way for liquid to move. Okay, it has to move to this direction. Okay, so vapor is moving in upward direction through this chimney. Okay, and there is a certain gap between cap or this cover and this riser. Okay, so vapor is moving upward, and through this gap vapor moves in this horizontal way, and then it passes through these holes. You can say this is the hole, this is the hole. Okay, this is the hole. So vapor passes through this hole. Now what happens when vapor passes through this hole? It passes in what we can say, in certain bubbles. Okay, the whole flow is not occurring as the vapor. Okay, but that vapor passes through these holes, and then it converts into the small bubbles, and therefore it is called as bubble cap. Okay, this is the cap, or this is the cover where holes are available. Okay, these holes are available. So vapor is coming from the bottom, moves upward through this riser, and beyond the riser it moves in this way, and then it exits from this hole. And as it exits from this hole, it interacts with the liquid. Okay, it interacts with the liquid, uh, what we can say, like it is in co-current. Okay, or vapor, when it is coming from here, it is in counter current with the liquid, because liquid is moving through this way over the plate. Okay, so in that way we can consider that vapor first interacts the liquid in parallel way, and then after that it will move upward. Okay, then it has the cross flow. Okay, so in that way what we can consider, that in a bubble cap tray there is a riser, which we call as chimney, and there is a gap between cover and this chimney, or we can say the cap, between cap and this chimney. And each cap has certain bubbles, oh, sorry, certain holes. through these holes, when vapor is moving, it is it converts into the small bubbles, and those bubbles are interacting with the liquid which is available over this tray. Okay, I hope you are getting my point. Right. So in this way, you can understand the mechanism of this bubble cap tray. The cap is mounted so that there is a space between riser and cap to allow the passage of vapor. As you can see over here, there must be a gap between cap and riser. Okay. So if you see, these are the in this way you can imagine the cap. Okay, these are nothing but the cap. Okay, so some vapor moves upward and some vapor moves through these holes and converts vapor into small bubbles, and that bubbles interacts with the liquid. Okay, so vapor rises through the chimney and is directed downward by the cap, as you can see over here, finally discharging through slots in cap or holes in cap, and finally bubbling through the liquid on the plate, as we have already discussed. So this is nothing but the bubble cap tray, and this is the traditional and oldest type of cross flow plate. Okay, cross flow we are saying because it is once it is coming once it is exit out from here, it has the parallel movement and then cross flow. Okay. Right. So in this way we consider the that bubble cap bubble cap tray. Now uh, how you will consider the flow where weeping is not occurring. Okay, so just you can see this type of plates. This is basically the bubble cap, and these are the bubbles. Okay, so the most significant feature of the bubble cap plate is that the use of risers ensures that a liquid level of the liquid is maintained on the plate and all at all vapor flow rates. Okay, now what happens when this riser is available and when liquid is flowing through this over this tray, then what will happen? Liquid is liquid is not allowed to move to this direction through this hole, and because of this riser, liquid cannot come to this direction. Okay, and therefore weeping will not occur, whatever would be the flow of the vapor. Okay, therefore we consider that if vapor flow is very low, you should choose bubble cap tray. Okay, otherwise not, because you can understand the bubble cap tray looks like this. So it has less uh, bubbles, or what we can say less holes, and because of this bubbles, the manufacturing of this bubble cap tray is very high in comparison to sieve plate. Okay, and therefore it is not it should not be used until unless it is not mandatory to use, and that mandatory part will come when I'm dealing with very low vapor flow rate. Okay, so in this way you can consider that uh, weeping can be addressed, but obviously manufacturing cost will be too high for this. Okay, so in this way you can consider the bubble cap tray. Okay, now as you know that sieve plate is very cheap, very simple, but it has weeping condition to occur. Okay, possibilities are higher. Okay, that we can address through bubble cap tray, but that is again very costly. Okay, so is there any tray which is available in between two? Okay, the answer is yes, and that is valve trays. That is valve trays. So valve trays or plates are the advanced version of sieve plate. It contains larger diameter holes. Okay, so larger diameter holes, so more what we can say vapor, what we can say larger flow area is available for vapor to move. Okay, and because of that vapor can move upward easily. Okay, but as it is the same called as sieve plate, advanced version of sieve plate, uh, so it should also operate at low vapor flow. Okay, what is the point to consider? That it should have the uh, provision to consider the vaping condition, but it should not be of very high cost. Okay, let's see how it will happen. So the valve tray perforations are covered by liftable caps. Okay, if you consider these bubble caps are simply sit over the riser. Okay, sit over the uh, riser which is attached to each hole. Okay, so because of these bubbles, okay, there is a provision for vapor to move from here and there as we have just discussed, but in no case this bubbles are allowed to move up or down. That stay bubble cap is stay on its position only. Okay, however in uh, valve tray, we have the liftable caps. Okay, liftable caps are not available in bubble cap tray. Okay, I hope you are getting what I'm trying to emphasize on. I'm that only so far we have covered 3 4 slides only, but this explanation is required for you to understand the exact working of the trays, each type of tray. Okay, so valve tray basically has the liftable caps. Okay, flow lifts the caps and thus self creating a flow area for passage of the vapor. Okay, so basically this is nothing but the what we can say the valve trays where you cannot see the holes uh, right now. Okay, you cannot see the holes because each holes are covered with this liftable caps. Okay, here you can see very clearly that bolts are available, and because of these bolts this tray um, are what we can say these are fixed at inner periphery of the column. And here wherever the you are finding the uh, joining of different sections of the plate, there holes are not available. Okay, at the periphery holes are not available. Here also if you visualize, holes are not available. So in this image you can visualize the uh, what we can say the coming zone very clearly. Okay, instead of the diagram where I have discussed. Okay, so let me first show you the holes as well as these liftable caps. Okay, so if you see, these are the holes. Okay, and here I'm having liftable caps. Okay, these caps are simply stayed over here, and as the vapor move upward, okay, vapor coming from these holes, these vapor lifts the cap upward, and it has the movement of the or the flow area which is available for vapor to move. Okay, so once vapor lifts this cap, it will come through this flow area and then interacts with the liquid. So again it has the horizontal interaction along with the cross flow interaction. Okay, so horizontal interaction and cross flow, it gives better mixing over the plate. Okay, so in this way, horizontal movement of the vapor is more prominent in comparison to bubble cap tray. There also it happens, but here it is happening easily. Okay, because the bubbles are not available. If you see these caps, these are liftable caps, and vapor passes through these holes. Okay, so you can argue that there is no riser. So what is the phenomena for liquid to stop to coming to the holes? Okay, because this cap will only move up with the vapor, it has nothing to do with the liquid. Okay, and as the vapor moves up, it lifts the cap, and the vapor coming from this. Okay, however, if vapor flow is low, okay, if vapor flow is low, the vapor is cannot move this cap upward. Okay, so the point is, when I'm dealing with low vapor flow rate, vapor cannot um, cannot move or cannot lift the cap. Okay, and therefore if that cap will not move upward, liquid cannot move downward. Okay, so in that way we can have the um, that valve tray which cannot be operated at very low vapor. Okay, if low vapor will be there, certain amount of opening is possible through which vapor will move, but as far as liquid movement will come to through the hole, that is not possible, because it will occur only when the vapor flow rate is very low. Okay, and when the vapor flow rate is very low, that cap will not move up. Okay, cap will not move up, so that liquid will not allow to move down. Okay, similarly for high flow rate, where the it will vapor will open the cap, or lift the cap fully, but this cap will stop over here, as you can see the assembly. Okay, beyond that it cannot be opened. Okay, so very low vapor, cap will not open up. Very high vapor, uh, what we can say, valve will be opened, it's up to its full height. Okay, but it does not allow to move up. Okay, in this way you can see the this each cap. Okay, this is the liftable cap. So if you see here, bubbles are not available. So as vapor moves up, it lifts the cap and come across or come out from this gap, which are much more than the bubble cap. Okay, so bubble cap has a different advantages, because it is converted into small bubbles. The vapor is converted into small bubbles, and that interaction is possible. Okay, however, in this case, because of the horizontal and cross flow movement, better mixing we expect. Okay, because it has vapor is coming from these, and then horizontal and then vertical movement will occur. Okay, weeping will stop, because at very low vapor, valve will not open up. Okay, so the liftable cap directs the vapor to flow horizontally into the liquid, and thus providing better mixing than is possible in sieve plate. Okay. The valve tray can operate efficiently in lower flow rate than sieve plate. The valves closed at low vapor rates. Okay. So vapor flow rate, if it is less, valve will not open up. Okay, in this way you can see more closely the openings. Okay, from the if operation is not going on, you cannot see this. You cannot see the holes. Okay, because these are generally closed with this liftable caps. Okay, so in this way we can have the advantages and disadvantages over the plate of each type of plate. So manufacturing of this is again costly in comparison to sieve plate, but in comparison to bubble cap, these are less. Okay. However, if I tell you that um, what about the pressure drop? Okay, pressure drop, you can understand that wherever the friction is more, we have more pressure drop. Okay, so friction is least in sieve plate, so pressure drop is least in sieve tray. Maximum pressure drop you can observe in bubble cap. Okay, and medium will be occur in valve tray. So you can see bubble cap is very costly. So you can use the bubble cap only in the case when you are having very low vapor flow. Okay, here you cannot handle very low vapor flow rate, though it does not allow liquid to move down, but at the same time it will not the valve is not open up. Okay, and therefore the any type of operation is not possible. Just 1 minute, please. uh, Yes. So in this way, we can consider different plates and respective advantages and disadvantages. And the only thing is the maximum operating range, if you are considering for vapor and liquid, the maximum operating range you can find in bubble cap. Okay. But in this valve tray, uh, the operating range of vapor and liquid should be much more than the sieve plate. However, sieve plate, because it is very cheap, it is very simple. Therefore, we used to consider that if the operating condition allows. So first, firstly we should consider the sieve plate and then wall tray and then bubble cap. Okay, so in this way you can consider the different types of plate contractors, and we will proceed further with the liquid distribution. Okay, okay, liquid distribution or liquid pattern over the plate. Okay, so here I'm having different things like when I say that liquid is moving from inlet downcomer to outlet weir. Okay, inlet downcomer to outlet weir. Okay, if you see liquid is coming to this calming zone, inlet downcomer. Okay, and then it flows over this plate and exits from here. This is outlet wear, inlet downcomer to outlet wear. Okay, so when I'm considering that, this is called as the single uh, flow or single pattern of liquid to move. Okay, it drops, it comes down here, moves over here, exits from here. Simple. Okay, so that type of pattern we call as single pass pattern. Okay, or single pass plate we call that. Okay, so that is usually we do. Okay, normally we consider single pass. Next we have the reverse flow of plate. Okay, reverse flow of plate, like here I'm having this as we have the baffle. Sorry, as we have this weir in the similar line, in that case if you consider the, let me tell you, I hope it will be clear from here. Okay, let me tell you like this, that in this case liquid is falling to half of the calming zone of this side. Okay, and here I'm having this what we can say, one strip is there which you can consider as the baffle or the weir, and this is the exit weir. Okay, so in that case this is the complete plate. Okay, complete plate, and this one baffle which I am talking about, this will be welded over here. Okay, that welded or wear will be here. Okay, and this is the section where the solid part is available. Okay, as it is shown over here, but this section, it is completely removed. Okay, or hole is available over here, right? What is the point over here, that when we are considering reverse flow, the inlet downcomer and outlet wear both are available at the same side. Okay, in usually in single pass what happens, the inlet downcomer is at one side, another side outlet wear is there, but here we are having inlet downcomer and outlet wear both are at the same side. Okay, and this is when liquid is coming to here. Okay, it moves in. Okay, it moves towards this. Okay, reverses its direction and then exits from here, right? So in that way we consider the inlet and outlet both are at the same side, number one. Number two, when this type of flow will occur, when I'm having like very less flow rate of liquid. Okay, if liquid flow rate is very less, and if I consider the single pass, it will not cover the whole plate. Okay, therefore we reduce the flow area, we reduce the flow area by half. So initially it will pass through this whole, reverse back and then exit from here. Okay, so this reverse pass Reverse flow plate, it will occur when I'm having very low flow rate of liquid, not vapor, liquid, because liquid has to move over the plate. Okay. And thirdly, I'm having double pass plate. Double pass plate is used when I'm having very large diameter of the column. Okay, then also the single pass, it will not cover the whole. Okay, liquid will not, whatever would be the flow, liquid will not able to cover the whole plate once. Okay, therefore in this type we consider double pass plate. Okay, liquid, this is inlet downcomer and this is outlet wear. Okay, so liquid will move from here to here like this. Sorry, like this. Okay, so in this way you can consider double pass plate. More closely you can see like this. Okay, in the first plate liquid is coming to this section. Okay, from the above plate, sorry, not first plate, from above plate liquid is coming to this section, moves in this direction. Okay, liquid is coming to this section and moves this direction and then exit from here, then exit from here. Okay, and if you can see here, we are having the gap, so through these gaps it will move here and then exits from here, exits from here. Okay, so in this way you can consider double pass plate. This is used when we are having very large diameter of the column. Okay, this is used when we are having very low flow rate of liquid. This we use normally. Okay, so in this way we can consider the liquid flow pattern and different types of flow contactors. And now we will start the another part of the design, and that is plate hydraulic design. How to design a single plate. Okay, and how to design different parameters in this plate. Okay, so let's start this. Just one moment, please. Yes. So this plate hydraulic design, we will consider the design procedure for a plate, and it is a trial and error approach. Where this trial and error will come, that we will see. Now the procedure is, we will discuss some steps over here and then we will proceed towards the example. Procedure is like, number one, we need to calculate the maximum minimum flow rates of vapor and liquid considering turn down ratio. Okay, usually when we consider the design of distillation column, we are given with V and L. Okay, what is the vapor flow rate, what is the liquid flow rate, that is the known quantity, right? So uh, this vapor and liquid, that movement we consider in a range. Okay, why the range? Because maximum flow of vapor will decide flooding, minimum flow of vapor will decide weeping. Okay, and uh, whatever flow we are given, vapor and liquid, that we consider that we usually consider as maximum flow. Okay, so what should be the minimum flow that we count, that we calculate considering turn down ratio? Turn down ratio is basically the ratio of maximum flow minus ratio of maximum flow to minimum flow. Okay, so whatever is given to you in the problem, it is usually that it is maximum or minimum what, but you, if nothing is there, we can consider that as maximum flow. And considering turn down ratio, we calculate the minimum flow. Turn down ratio are usually given to us, like it is 70% or 75%, like that. Minimum flow should be 70% of maximum, something like that is given. Okay, so turn down ratio will be given to you. One of the flow will be given, so you can calculate another flow. Okay. Further, we collect the physical properties, and physical property we usually consider at different temperatures, like when we consider rectifying section or when we consider stripping section, temperatures are different. Okay, so those temperatures we can consider to collect the physical properties. And uh, that physical property you can also find how you can collect the physical property, which we have already discussed in shell and tube heat exchanger, right? So in the same pattern you can discuss, but temperature should be location wise. Rectifying section hai, it is rectifying section or stripping section, whatever. Okay, next step is we need to select the plate spacing. Plate spacing, we I have discussed that distance between two consecutive plates. So that would be trial, because you need to assume any value. Okay, so plate spacing moves from 0.15 to 1 meter, which are normally used. Okay, so you can choose the plate spacing between this range, but to a better start, we have like 0.5 meter or so plate spacing. 0.45, 0.5, like this you can consider. Okay, next is we need to find out the column diameter based on flooding condition. Okay, as you understand that flooding condition basically counts the maximum vapor flow rate. Okay, and when the flow rate of vapor is maximum, it covers the maximum uh, there is a possibility to cover the maximum area of the distillation column. Okay, flooding velocity will be decided based on maximum vapor flow, and maximum vapor flow will spread in the maximum cross section area of the column. Okay, so once I decide the flow rate considering flooding condition, we are already aware of the uh, what we can say, the flow area V and L, that you know already, which you have already decided in this point one. Okay, and here you can calculate the velocity at which flooding will occur. Okay, so division of these two will give you the area, and that will we use that area to find out the column diameter. Okay, so that point we will also discuss in detail further. Now, next, we need to decide the liquid flow arrangement or liquid flow pattern, as we have seen single plate or reverse plate, double pass, whatever. So based on that, you can decide the flow range. And next, we need to decides the layout of the plate, like what is the downcomer area, active area, hole size, and wear height. Okay, downcomer area, that it is usually in percentage of column area. Active area, you know that total cross sectional area minus twice of downcomer area. Whole area, that it will that whole area of a single whole size, when I'm considering that how much opening for the whole over the metal plate will be done, that we can see, and wear height. Okay, so all that these parameter we will decide. How these will be decide, that we will see. Just a moment, please. Sorry for in between interruptions. So once I decide the plate layout, we can check for the weeping condition. If weeping condition is not satisfactory, we will return to step 6 and decide hold size and other parameter. How we should check the weeping condition, and what are the ways to mitigate that we will discuss. Okay. Now then we will check the plate pressure drop. If too high, we need to consider the step 6. Okay, because plate pressure drop is again the important parameter to have the flow of the liquid over the plate. Okay, so it should not be too high, and if too high, we need to adjust the parameters in step 6. Okay, that we will see. We need to decide the, we need to consider downcomer backup. If too high, again is step 6 or 3. 3 is where we have decided plate spacing. Okay. Next, we need to decide the layout design, like over the plate, how much, what is the calming zone, perforated area, and check for whole pitch or whole spacing, the same thing. Okay. If unsatisfactory, return to step 6. Then we need to recalculate the percentage flooding based on chosen column diameter. Okay. Actually, when we calculate the column diameter, and if standard diameter is available in the market, we need to choose the standard diameter. Therefore, we need to consider the percentage flooding again. We need to calculate. Okay. How all these will be done, that we will discuss. And then we will check for the entrainment. If too high, we need to return for step 4. That is the flooding percentage we need to fix again. Okay, and then we can have the optimum design. In this step 3 to 12 will be repeated to find out the lowest cost plate. Okay. So in this way, we will consider the design of plate, and I'm stopping over here. We will start detailed discussion on plate design from the next class. Okay. And if you have any confusion, please discuss, or let me know if you have any observation. And that's all from my side for today. Okay. So if you have any point, you can share.
No, ma'am. Thank you, ma'am.
Okay. Thank you. So thank you all for your patience. Thank you.